You know, when Marcus confirmed that we are going to have a presentation done by Professor Gaunt, I said to myself, wow, I hope I'm not going to be scheduled to go somewhere on site where I will not be able to connect, because I really need to listen to Professor Gaunt. And again, to many of us, we know Professor Gaunt. In my view, I'm not even worthy, to actually introduce him. But anyhow, because today I'm chairing the session, so I will introduce Professor Gaunt. Prof.
Good afternoon. I hope you can all hear me clearly.
Wonderful. We can see your face, Prof. Your audio is loud and clear. So thank you for that. Just quickly, let me just introduce Prof. Prof today will be talking to us about a new approach to defining, measuring, and controlling electric power. I think the key word there is new, new approach. So we really need to be listening carefully to this. So for those who probably do not know Professor Trevor Gaunt brings with him more than 50 years of experience in the utility, engineering, consulting, business, and academia. Many of our people have been lectured by Prof, trying to analyze and solve some of the complex power problems. So he has encountered many inconsistencies in diverse topics like electrification. We know that he played a major role on electrification in South Africa, tariff designs, geomagnetically induced currents, and he also joined Michel Malengret in looking for a better power theory. So in 2020, they published the general power theory in the frequency domain, and this was followed by a two-part paper in Secret Science and Engineering. His present interest is in supporting the development of physics-consistent measurement and control and in their applications. So by so saying, then, colleagues, I now hand over to Professor Gaunt to take us through his presentation on a new approach of defining and measuring and controlling electric power. We're really looking forward to this presentation, and we're going to give Prof a chance to go through the entire presentation, and then at the end of the presentation, we'll then open for Q&A. Thank you, Prof. The stage is yours. Over to you.
Thank you, Lloyd. And greetings to all of you. Many names that I recognize in that agenda for the meeting. So greetings to you. There are a few of you who heard a similar presentation in a different setting with a different objective. And I apologize, you can go to sleep in the few parts that you already know. For the rest of you, I'm hoping this is really going to wake you up. Right, very quickly, I'm going to run through some of the background leading to the comments that I have about load research and load modeling. So the objective of this presentation is to give you some information and then draw it to the application of load research. I'll talk about the background, the problems, and a solution to those problems, and then we can move on to the applications and the next steps. So the objective is to clarify the modeling of loads and sources, because sources are negative loads, in the context of electrical power systems. That sounds really odd. It's what you do all the time, but I'll show you that it isn't. Very quickly, we're in a situation where there is a lot of technological change, new energy sources, distributed generators close to the grid edge, which actually change the distinction that we have between transmission, two ways power flow up and down the line, and distribution, always thought of as radial. A huge introduction of power electronics in both loads and sources, new applications facing us, EVs, battery storage, data centers, a whole lot more. And digital techniques in relaying and control and protection and metering. So the world that we have today and looking forward just a decade is hugely different from what it was 20 years ago, 30 years ago, when we were talking about load modeling for the NRS standards and the electrification program in South Africa. At the same time, there's been a structural change. The vertical monopolies that we've had in Eskom and the municipalities are quickly changing into markets and hybrid structures. So we're not market orientated. We're no longer monopolistic. There's something in between, and it's not defined. We have increasing competition and changing regulation. If you haven't commented on the electricity regulation bill, perhaps you should think about it. And it differs everywhere. What's happening in South Africa is not the same as what's happening in the rest of Africa or in the rest of the world. And these things are bringing problems. There are problems in making measurements of apparent power and reactive power and power factor that are being reported from all sorts of different directions and landing some utilities in the courts. They give inconsistent quantities or values for the quantities measured. If you take out one meter and put in another, you don't necessarily get the same reading. And the reading that you're getting is not interpretable in terms of physics. I'll come back to that later. And this is what leads to the disputes. We have problems with inverters supplying unbalanced loads. We have a problem identifying optimal operation, both in steady state and transient. And that leads to system failures. And I'm not talking about load shedding. I'm talking about systems going down because they're unstable, they lose synchronism, things like that. And behind all of this, we see, if we're familiar with the literature, many, many researchers still looking for new theories to cope with all the technological challenges that are coming up. Because errors and approximations in control and analysis and in metering incur costs for somebody, either the supplier or the customer, or sometimes for both. So let's look at some of these many power theories. It goes back a long way. The first was probably formalized by Kennelly in 1910. He was the Prof of Electrical Engineering at Harvard University. He proposed a single-phase power triangle and the concept of vector power. That was 114 years ago. It's available in the IEEE Explore sites. That was followed by a lot of other people coming up with alternative standards, not standards at this stage, alternative ideas, systems, theories. Buchholz in Germany took a very different approach. He looked at the three-phase unbalance of apparent power, and what he defined was a null point. Now, at the time, the AIEE, now IEEE, was proposing a quite different way of identifying the reference point for three-phase apparent power measurements. Budianu in 1927 suggested a way of looking at the waveforms with distortion, and he proposed using the frequency domain. And that was completely thrown out by Frieser, a German researcher, and he looked at non-active currents in distorted systems, but not in the frequency domain. These were followed by Deppenbrock, who published papers which were basically termed the Frieser-Buchholz-Deppenbrock theory, and Sarnecki, who came up with the current physical components theory. Then in 1983, Akaji came up with the instantaneous power theory. This was a response to the growing use or applications, experiments sometimes, of power electronic devices. And he was followed by his co-author, Nabe. So the first one was Akaji and Nabe. Then Nabe published a modified PQ theory, and much more recently we have Samos with his enhanced PQ theory. At the same time as those were developing, you have Tenti and his co-authors in Italy. You have the publication of the IEEE Standard 1459, which replaced the earlier standards on power theories. Came out in two versions. There was a lot of preliminary publications in 1997 through to 2000. There was a draft version, and then 2010. And that is now redlined, meaning it's no longer valid. And then, to make matters worse, if you look at it that way, or to try and solve the problem, Malengret and Gaunt weighed in with the general power theory, first in the time domain, and then in the frequency domain. So there we have it. The instantaneous theory is used for inverter control. The general power theories, all based on an apparatus as a part of a system. An apparatus, the equipment connected at a point of connection. It can be a load or a source or another network, but we give it the general term an apparatus. And then Malengret and Gaunt doing something completely different. They looked at measurement in the context of the whole system. In other words, the measurement model included the apparatus and the delivery system. That was their solution, called the general power theory. It's based on the physics of circuits, names you'll recognize: Ohm, Kirchhoff, Helmholtz, or Thevenin, depending on whether you come from a German or a French background. Energy, the law of energy conservation, and it measures the power parameters of a load source or network in the context of the whole power system, the source, the equivalent delivery system, and the apparatus. So it's a completely new paradigm for modeling steady state and transient performance in AC and DC systems with any number of wires, with distortion and with unbalance. And it leads to parameters for metering, including apparent power and attributable delivery loss and power factor, and parameters for control. That includes things like the efficient power delivery, compensation currents, and in control of compensators and inverters, and it doesn't require reference frame transformation. We'll come to that again later. So this is the model. Instead of having just the apparatus and measuring only at the point of connection with a source at that point of connection, which is an ideal source, we model the rest of the system. So we can make measurements of the instantaneous currents and voltages, which give us the power at the POC, and we can also derive the complex root mean square, magnitude and angle. Complex because it's magnitude and angle, RMS because we're looking at the RMS values of sinusoids and not at the peak value. And we do that for each wire, M, and each harmonic, H. So what we're looking at is taking that distorted signal at the POC, using a Fourier transform to identify the frequency components, and measuring the impedance from the POC looking into the delivery system. So what do we do with that? So in this picture, I have an equivalent subsystem for each frequency component. So now this is the system for a frequency. It could be for DC, or for the fundamental frequency, or for any of the harmonics, second, third, fourth, we separate all of them from each other. And we know that we can add the power up as scalar quantities. So let's replace that with a conventional system diagram. We take the measurements of voltages at the reference point, at the POC, point of connection, and we measure U, and we express that as the RMS value of magnitude and angle. From that, we can look back through the equivalent impedance to the voltages at the equivalent source as measured from the point of connection. Then we look at step 4, calculating the voltage source from a reference point at the voltage source. And that reference point is defined by Kirchhoff's voltage law. And finally, we can allocate currents, the optimum set of currents in all those wires, depending on whether they are high resistance or low resistance, and the voltage source for each wire. And we can allocate the currents as the most efficient for delivering the power in terms of the delivery loss, the total delivery loss. For those of you who are mathematicians in your thinking, this is a transport optimization algorithm, where you look at the distribution of different pathways with a total cost in terms of losses or finance or something like that. And then finally, we can calculate currents for compensation if we put a compensator into the circuit. That's a very quick run through of the theory. Although it's developed in linear algebra, which most of us forgot after we learned it in second year, did the exams, and then never saw an application of it again. And I was in exactly that position when I started working with Michel Malingret, who really is a mathematician, and I had to relearn all that linear algebra that I'd forgotten a very long time ago. But what comes out of it are arithmetic calculations that you can do easily on a spreadsheet. By easily, you use add, subtract, multiply, divide, cos and sine trig functions, and that's it. So it's a very easy calculation to do in a spreadsheet or a programming language or on a microprocessor. Some outcomes of the theory. Now, this is where you really need to wake up. Reactive power and energy only exist as operational definitions. They are what some person said you must do to calculate a number. But that number has no physical interpretation in a practical system. It is not a measurement that is representative of what is actually flowing in the system. It is a measurement that is made according to an equation defined by someone. The other I mentioned earlier is that the Thevenin voltage offset at that equivalent source happens to be consistent with the approaches of Buchholz and Deppenbrock and Sonecki, but not with those of many of the other power theories. And it's consistent because it applies the Kirchhoff's voltage law in identifying a null point for voltage measurements around a circuit. And if you just take any arbitrary voltage reference point, because you can measure voltages from any point in a system, you can measure it from the doorknob. And those voltages will be the voltages, and you can use those voltages to calculate the total power. But you cannot use them to calculate the power applicable or attributable to a particular wire and frequency domain. So those other voltage reference points, including a neutral wire, introduce ambiguity and uncertainty and error in making measurements. In other words, the measurements are not physically interpretable. they are measurements, that's fine, but you can't say it has anything to do with the power flow in the network. As I mentioned, because we separate the whole system into the frequency subsystems, we get the scalar sum of power. So the power at DC plus the power at fundamental frequency plus the power in the second, third, fourth, and fifth harmonics can be added, taking into account their direction, positive or negative. Positive power flow is into a load. Negative power flow is out of a source. And that's all. Power can't have a direction orthogonal to the wire. It can either go into the load or out from a source. Now that means that compensation currents are not orthogonal to the active current at the point of connection, because when we allocate the currents to minimize the total costs, we are going to change the voltages at the apparatus at the point of connection. And if the voltages are changing, then you can't have it that the compensation current would be orthogonal to the active current. And that means that conventional unity power factor, measured with current and voltage in phase with each other at the POC, cannot incur the minimum loss for power delivery. So if somebody says to you that for optimum power delivery, we need to align the currents and voltages, in other words, get them to unity power factor, that is not the lowest cost. Not what we taught you, and I apologize for those of you that I taught you the concepts of reactive power and the implications of it, because I was wrong. I have learned something since I taught you that. Finally, we can define an apparatus case, which is the assumption of an ideal source at the point of connection, which allows us to compare with all other power theories. And what do we find? Except that it gives the same values as for apparent power at the apparatus and the power factor at the apparatus, consistent with effective apparent power and effective power factor as defined in the IEEE standard of 1459 of 2010 and as used by Czarnecki. So we're not a million miles out, but by adopting this new paradigm of looking at things in the context of the delivery system, we come up with very different values. Right, it's not just a theory. We've looked at it in simulation testing. Here is a particularly troublesome example on the top left. We have an inverter driving a rectifier driving a variable speed drive for a motor, and we unbalance it with this 300 kilowatt load connected between phases red and blue. And the unbalance in the wire currents is really evident before compensation, and after compensation, it moves very quickly to being a compensated current. And the compensating currents, bottom left, are very different from each other in the three phases. And that's what trips up the PQ theory, because it's unable to look at unbalance. And that distortion that you're getting there introduces harmonics, even in a system with no harmonics in it, no nonlinear loads. We carried out a study of distributed generation. Here is a very simple feeder fed from the left by a bulk supply with at bus 6 a 3,000 kilowatt renewable energy source, which is fed into the system with a converter, what we call converter interfaced generation. And as you probably all know, as that injection from the DG increases, the voltage rises from the dotted black line, which is the voltage profile of the passive feeder, until it's eventually pushing power back into the feeder, and the voltage at the far end of the feeder rises. and it can rise beyond the limits of acceptable operation. One of the things that happens then is that we invoke fault-far compensation to suppress the voltage rise, but that gives rise to very large losses. So that red dashed line is the increase in losses above 2 megawatts of input DG, and it very quickly increases the quantity of power that needs to be imported from the bulk supplier at the far end just to make up for the losses. The issue then becomes, who should be paying for the excess losses that occur when a renewable energy generator invokes fault-far compensation? The customers aren't getting the energy, but the DG is pushing it out into the system. It just warms up the wires in the atmosphere, and somebody has to pay somewhere. We've also looked at it in terms of practical testing. We've carried out physical tests and controller and power hardware in the loop experiments. So the way we did this is we designed a completely new 20 kilowatt three-phase four-wire inverter at UCT. We assembled it. It's a three-level inverter, as I say, 4 wires. And that inverter is controlled using the general power theory. Then skipping to the bottom, we modified an 80 kilowatt three-phase 3-wire inverter, which is made, it's a commercial inverter made by Area Meta Power, who are based in Kempton Park. And then we took that inverter, the 80 kilowatt inverter, to Strathclyde for testing in their laboratories there, but it was held up in customs, in delivery. And what we did instead was we modified in 3 days a 10 kilowatt three-phase 4-wire inverter belonging to the University of Strathclyde. And so we carried out tests on that one, as well as on our own 3-phase 4-wire inverter and the factory tests on the 3-wire inverter. Let's look at some of those. There's our, during assembly, 20 kilowatt inverter on the left-hand side. It's surprisingly compact because many of the things that it can control allow the size of the inverter to be made quite small. And you can see the controller in the foreground of that inset. On the right-hand side, a much more sophisticated laboratory. This is the power hardware in the loop testing at the Dynamic Systems Power Laboratory at the University of Strathclyde. On the left-hand side through the window, you can see the power supplies, and then there are various cabinets providing the inverter and the inputs to that inverter. This is a picture of the Area 80 kilowatt inverter, which we did a little bit of testing in Scotland when we did eventually get hold of it, but most of the testing of that was carried out in the Area factory in South Africa. And 1, 2, 3, 4, 5, 6, 7, that's the 6 is the converter, and the rest of it is the test setup. And those tests were described at the Seagrey Regional Conference in October last year. Right, so what are the applications of the general power theory? Obviously, to meters. It's necessary to meter physically interpretable power quantities. So we can't measure reactive power because the definition of reactive power is not physical. And therefore, if it's not physical, we really shouldn't be charging for reactive power. So we can identify measuring power and energy and the direction of harmonic power flow, which has all sorts of implications for those studying power quality. In terms of control, we can optimize the delivery loss. We can prevent harmonic pollution coming from a rectifier. For example, if you have a pretty standard rectifier. It injects fifth and seventh harmonic power into the system. We call it a harmonic source. And the GPT immediately blocks that under its control, because injecting power into the system, which is only going to lead to losses, and importing the power at fundamental frequency, which is the source of the harmonic pollution, incurs losses. So it finds currents that don't allow those losses. You can also apply it to control of active filters for multiple harmonics, and energy can be actually converted from a harmonic power into a useful fundamental frequency power. And some more simulations and tests are carrying on in that area. And finally, or not quite finally, but the implications of the first two are that it changes our electricity regulation. So based on physical performance and losses caused by unbalance and distortion, the regulator has to start saying, this sort of tariff is acceptable, this sort of cost allocation is acceptable, and this sort of power quality regulation is acceptable. And our regulator is a long way from doing any of that. So are many other regulators in the world. The challenge to the regulators are that the traditional theories can't model apparent power and power factor in the presence of unbalance and distortion at a meter, particularly a transmission system operator or distribution system operator. And then there are a whole lot of other problems that stem from the fact that apparent power and reactive power and conventional power factor are not physically definable as affecting losses or the performance of the power system. The conventional power factor can only describe the phase displacement between voltage and current at the point of measurement. So standards and regulatory uncertainty affect the utilities, customers, analysts, and equipment suppliers, but they also affect those doing load research and using the results of the load research. So let's look at what we can and cannot do. We can take a current model and we can use current and voltage and the angle between the currents and voltages, and we can separate it into the frequency components, which are sinusoidal signals then, and that is completely acceptable. We can measure impedance. Impedance is a scalar. Z is made up of resistance and reactance at whatever frequency you choose, and you can define an impedance factor, which is R over Z. And if you look at that, it looks curiously like the factor which we call power factor, conventional power factor. And so maybe there's not such a difference there when you're looking at impedances and currents. But when you come to power, you can measure power and energy. Those are physical quantities. But you can't usefully measure reactive power. Sure, you can measure it. You can apply any equation you like to a measurement, but it doesn't mean anything in terms of the system performance. And we can measure apparent power for an apparatus, assuming that the supply to that apparatus, hard on the terminals, is a nice ideal voltage. It's at the rated voltage, it's balanced, and it's sinusoidal. And that's what the definition of S is. But that is not defining a load. That is defining something which is a parameter of the apparatus that you've connected to it. Because if you change the voltages or the impedance of the system supplying that apparatus, you change the conditions of the delivery system. And then S has got nothing to do with the performance of the delivery system. So when you're looking at clusters of loads, and this really brings us to the area of load research, I just want to summarize, first of all, three things that have been happening. The NRS Load Research Project measured LV load currents. Good. There was a justification for that because many of the loads were time dependent or energy dependent. So if you boil a kettle of water, it might be a 2 kilowatt kettle or a 3 kilowatt kettle, but it pumps in just that amount of energy over 1 minute or 2 minutes to 1.5 minutes to boil that water. And so it's really an energy device. But then there are some things, motors are power devices, and others truly are impedances. So the Load Research Project took the sort of happy middle in measuring currents, and that was very deliberate. It was the input to the Herman-Beta algorithm, to the Herman-Beta extended algorithm, which can be applied to MV loads and DG and includes loads which are not at unity power factor and systems which are not defined only by the resistance. So for that sort of application, you need to identify clusters by the beta PDF of currents and a fixed PDF, fixed power factor, or the impedance factor. Johannes or Lolo Base identified large power user profile customers by power in time of use. So the power at peak, standard, and off-peak times, the power factor or impedance factor, as I prefer to call it, and a half-hour load factor. And he was able to cluster the profiles then using these 5 parameters. And all of these measurements are made at variable voltage. When you talk about measuring the load, the power, the current, whatever it is, at the LV customer or the large power user, you don't have strict voltage control. So you're not really measuring the rated currents or rated power of those devices. And so we start looking at the probability density functions to look at the clusters. Then we need to say, well, what happens if we are controlling the voltage? So if you think of a high voltage system supplying medium voltage and low voltage systems through transformers with online tap changes, the bus bar where you're making the measurement in that sort of system is a voltage regulated bus. So you can, at that point, measure the impedance and the impedance factor, because what the OLTC is doing is changing the ratio, and therefore the impedance referred back to the supply side. So you can adjust Z by a voltage ratio. And if you do calculations that go across networks with several different voltages, such as in protection or system planning, you'll be completely comfortable with that process. And then there are, of course, voltage variable constant power loads, where you're interested in the power and the impedance factor. Now, this sort of thinking requires a completely new approach to instrumentation, to protection, and in your case, to the interpretation of load research data, its collection, processing, and application. And that's quite novel. That's a challenge that we've not tried to face until now. I have here some of the supporting documents. There are 3 journal papers on the general power theory, one in IEEE Access, which is an open access journal, and one paper published in 2 parts in Seagraves Science and Engineering Journal, in October 2003 and February 2004, and those are the access addresses for that. And then Batamba, or actually as we call him, Yankee, and a whole lot of others from Ario, published a paper at the Seagraves Southern African Regional Conference, and there are 8 more conference papers available on IEEE Explore. If you search for either Janke or Gaunt or Malengret, you'll start picking up those papers. Finally, I've referred to 2 papers applicable to load models. Lolo Base's paper in the SAIEE Africa Research Journal on medium voltage load clustering, and Justice Chiota's paper on a probabilistic approach to distributed generation. So that's what I have to offer you. I'd be happy to answer any questions.
Thank you very much, Prof. Again, for the very inspiring and important presentation. At the same time, it's thought-provoking, and we really appreciate it. And I think I agree with Justice on the chat group there when he says that this presentation, the information that you are providing is getting clearer and clearer with repeated listening. And I agree with that, Prof. That when one listens to this the first time, it's really a bit confusing to just take it as it is. But the more you present it, I think as a lecturer, you understand the concept that the first time in class, you might not be able to grasp the essence of what the lecturer is giving to the student. But the more the student go back to the lecturer, go to the textbooks and repeat that, then it's getting clearer and clearer what the lecturer was actually conveying to the class. Thanks, Prof. Is there any questions, comments for Prof Gaunt before I pose my question? Anyone who would like to comment or ask a question? And now is the time. Prof, whilst the members are maybe digesting on what you have given us this afternoon, you have mentioned there that the power that goes to the load and the power from the source is negative. I was trying to look into the power system from the source, because for me, the power from the source and the power into the load, in my mind, that's the same power. But then as I was trying to make sense out of this, I then said to myself, okay, in between them, there is, you will have the resistance and the reactance loss in between, which are causing some losses. And most probably that's why you are saying that it's not the same. May you please just clarify this, Prof, depending, just to make my understanding slightly clearer, because at the point of connection also, that is something that is critical for us, especially when you look at the distribution network system. Thank you, Prof.
That's a good question, Lloyd, because I think a lot of people struggle with this idea. The apparatus is what you are connecting as a load or a source or a network to the rest of the network. So this point of connection that we have are the terminals of your load, your household or your office building or whatever it is, your factory, or of your distributed generation, converter interface generation, maybe a small hydro, or a battery that is both a load and a source, or maybe it's even Kusile, because Kusile is really just a big apparatus. Well, a very big apparatus. Okay, but it looks into a system. And if you look at that system from the terminals of Kusile or of your battery inverter supply, you're looking into a system that has an equivalent source and an equivalent impedance. So by convention, we say if this apparatus is drawing positive current into it and positive load, then we call it a load. And if it's a source, we call it a generator. And then the power is negative because we've conventionally said positive power is into a load for the purpose of defining direction of flow in those wires. Now, what people very often struggle with is if I have a load which is a rectifier and an impedance behind that rectifier, and it is drawing fundamental frequency, then the fundamental frequency power flows into the rectifier and the load. And that's fine. But we talk of this as being a source of distortion. So the same load is injecting fifth and seventh harmonic power, quite typically those two are the biggest, back into the system. In that respect, we talk of it as being a source. So the rectifier load is both a sink as a load and a source as a source of pollution. It's the same apparatus. And the convention we're saying is if the currents and power flow into the apparatus, that's representing a load. And it flows out of the apparatus, that's representing a source. Now remember I said, top right-hand corner, you have an equivalent subsystem for every frequency component. So this system for fundamental frequency is drawing power. But the fifth harmonic subsystem is exporting power from the same rectifier load. And the power flow then, because PPOC is defined as positive from left to right, the harmonic pollution power is flowing right to left, and we call that negative power, negative current. Does that help?
Yes, thanks, Prof. And I agree with Justice. The more you repeat these things, the more they get clearer and clearer. It's really interesting. At the moment, I'm trying to get a clearer and better understanding of the inverters, particularly for the purpose of renewables, rooftop PV and the likes. This thing of grid following inverters and grid forming inverters, does it really mean anything significant, Prof, to the system? The type of inverter, whether it's grid forming or grid following?
That is a distinction that is useful because it the grid following takes the frequency of the inverter, the frequency of the system, and it matches the inverter output to the same frequency.
Yeah.
If it's grid forming, it tries to push a frequency which is closer to the set point frequency, in our country 50 hertz. So there are various things that happen in the dynamic and transient domains that make those different. Where the general power theory has a huge impact is that all those inverters use a PQ reference frame or a DQ0 reference frame, and they use either a Clark's transform or Park transform to transform the actual physical, the real voltages and currents into a fictional reference frame. In doing that, there are certain items of information, parameters of information that get lost even when you turn it back into the natural reference frame of ABC. In the general power theory, we do all the calculations in the ABC reference frame, whether it's converters or inverters, that's all the same. And so we do not need to take the time and lose the information that leads to some of the errors of the PQ and DQ0 reference frame combinations. That is, in fact, a much bigger difference that's brought about by the general power theory than the difference that comes from grid forming or grid following.
Yeah. Thanks, Prof. Those who are operating as network designers, these are some of the things that they need to take into consideration. And those who are doing load modeling, those who are involved in data gathering processes, I think this is important information that we need to consider as we continue with our line of works. I think this is a very interesting presentation. Prof, my last question, I'm not sure whether it's a question or a comment. When you say reactive power not physically definable, does it really take away the power triangle? What happens then to the power triangle? And again, in relation to that, in terms of the calculations or measurements, what do you mean when you say it's not physically definable? Can I only calculate it theoretically, but not be able to have physical measurements? Because you said then they don't mean anything. Can you please just clarify that for me? Thank you, Prof.
It destroys the power triangle because the power triangle is based on the concept that power is a vector, whereas power is a scalar. I've just said we add up the components of power for each frequency level and we get the total power. That's not a vector addition, that's a scalar addition.
Okay.
And if you measure power, you're measuring the product of the voltage and the component of current that is parallel with that voltage, in phase with that voltage.
Yeah.
That is a measurement of the amount of physical power. If you measure apparent power as being the product of two RMS quantities of current and voltage, that's not a physical measurement. That's not a theoretical equation. That is an empirical equation. Somebody suggested it. And if you try to measure reactive power, that's the product of the voltage and the orthogonal component of current. And anyone who's done second-year linear algebra will tell you that the product of two orthogonal vectors, the dot product of two orthogonal vectors, is always zero. So reactive power is physically or theoretically always zero. Empirically, we scale it. We say, we are going to define it like this, and we're going to give it a value of 1 or 2 or 15 or whatever it is, megavars, but it's not physical. It's an empirical measurement made up by somebody, originally by Kennelly, but many other people have extended it to three-phase systems and things like that. It's not a theoretical measurement. So the PQS triangle, sorry, it's not valid. Let's do a rethink. Let's think about power, a product which we call apparent power in conventional systems, but in the GPT, it's actually the power that can be delivered for the same loss provided you optimally distribute the currents. As a physical meaning, and you measure it in watts. And you and Justice should become lecturers, because then as you start repeating this, it'll help you to understand it.
Justice is
So
already
all the
in that
listeners
field.
today should be explaining it to other people, and then they will start to recognize where they need to think a little bit further and actually understand it, because this is theoretical and can be understood.
Yeah. Yeah. Thanks, Prof. I see there's a hand. Karen, your hand is up.
Hi, hello, Prof. Yes, obviously there's a lot of theoretical things milling around in one's head, but to translate it from the theoretical, which is already a little bit difficult to understand, to the practical, what is available at this stage in the measurement unit or measuring equipment available that planners can perhaps start using to try and interpret a little more than what we've been doing up to now. If you can maybe just try and make it a little bit more practical for us.
Okay, I'll try to give you some examples. Power meters in megawatts and energy meters in kilowatt hours or megawatt hours are valid. What happens is that many of them have been turned into smart meters, and you get energy flow in one direction or another direction, or average energy flow and things like that. And very often people don't understand what they're looking at. So you get a customer with only load, but it shows that there's exported energy of usually a small amount, comes up on the export register. But that might be harmonic power, which is being exported, whereas there's a whole lot more fundamental frequency power being imported. And there is a particular meter where I know that that has been happening. So the meters are able to measure the power and energy accurately. What often happens is that the displays are misleading, or those looking at the displays misunderstand them. There are several different methods of measuring equivalent impedances, and the voltage is derived from the impedance. So equivalent impedances, some of them are based on PMUs, others are based on passive change using Teligent's theorem, and others are based on disturbing the load and then making the calculation. The most obvious case of that is when you do a short circuit and open circuit test on a transformer. You're disturbing the load and you work out the parameters of the circuit. Michelle Malengret has started production of some devices which measure the Thevenin impedances of the network to which it's connected, but there are probably identified 30 other ways of doing it. We actually took out a patent on one of them and realized that that was an absolute waste, because if you patent one and maybe one or two others have patented theirs, there's still 25 more ways that can be used. So we dropped that. The university dropped that patent. Very few of the devices are commercially available because very few of the standards refer to them. So until utilities say, we want devices that can do this, manufacturers won't supply them as a standard device. I think that's about it at present. Obviously, frequency meters and things like that are in wide use.
What I'm hearing from you is that people must be more active on the standards committees to start insisting on proper measurements and proper, like, smart meters and so on, to be able to identify these things. Am I correct to say that this has a big impact on, identifying losses for choosing your current supply path and so on, and also for identifying what kind of losses customers and suppliers should be paying for. But is it also something that planners who look at the more longer term network systems, how can the planners actually use it? Sort of, I see it more as what I've said. The current supply, so you find that the best current supply route, but also identifying what the people have to pay. But for the planners, in our minds, it's a bit sort of further away. Am I right in thinking that?
You are, if you look at it conventionally. However, there are planners who are looking at the compensation for reactive power capability.
Okay.
So what is the reactive power capability that we must build into the system? And reactive power capability is like talking about the dragon's den. If you believe in dragons, I suppose it's probably okay. But if you take the view that maybe dragons are imaginary, then you have to find another way of looking at this. The techniques are there. If you think of Gauss-Seidel iterative techniques for load flow, we very often input the quantities as power and reactive power, but we immediately change them to voltages and currents. And the whole iteration is done on the basis of voltages, currents, and impedances. So there's nothing wrong with that. And Gauss-Seidel is very often the reference technique for looking at optimization in power systems. But a lot of the other systems, the equations, the load flow programs that we use really are based on this active and reactive power components. And those can be misleading. And one of the examples where it's really misleading is where we look at putting volt-VAR control onto a distribution feeder. And as soon as you do that, you're losing touch with reality and you're failing to identify who is responsible for the hugely increasing losses in that feeder. So where you said earlier, do planners need to know about it? In terms of applications of their conventional theory, they're very often missing what's really happening. And that gets carried through in the tariffs and the responsibility for costs and the grid connection agreements and things like that, for which planners are responsible. So yes, they do need to know about it. Yes, they are already applying it in many respects, but sometimes they're not. And I think with a greater understanding, they're less likely to make mistakes in future.
Thanks, Prof.
Yeah, thanks, Prof. I don't see any other hand. Prof, for me, I think from the load research point of view, what I'm taking away is that from your slides, you said that the load can still be modeled as current. And I think we will continue doing that. But at the same time, also, we are aware that the customer's behavior is changing. The load is also evolving. It's becoming more dynamic. And because of that, we need to be taking into consideration theories like this, the general power theory. We need to be looking into other parameters carefully for those who are involved in measurements. And I think also, Prof, the tariffs also are going to be impacted upon hugely for those who are designing tariffs. As you know, that historically, those who are designing tariffs will also rely on using data or information from projects such as Load Research that has been used extensively. I think now we need to be really careful on what we are measuring and how we interpret also these measurements. I think I liked your answer also to the question of Karen when you mentioned also the smart meters, which at this present moment, the smart meters are being rolled out. So I think some of the work that needs to be done by some of the like-minded who are sitting in this platform, I think it's high time that we also do something around that so that the data that is coming out can be able to be used effectively and properly. So, Prof, I really want to, on behalf of the Load Research Chapter and the Executive Committee members, would like to thank you for the time that you have spent with us this afternoon. You could have gone somewhere to other important meetings or family gatherings or spent time with yourself. Last time you informed us that by September you will be now officially retiring. And I know that because of the love and the passion that you have for this work, you might be tempted to even continue, Prof. But we really appreciate the contribution that you have made, to electrical engineering in all its many diverse facets. We really appreciate the theories that we have shared with many of us as we were sitting around the tables in many meetings. I remember some of those meetings in Megawatt Park, sitting around the table with Prof. Ron Herman, with Prof. Henry Selden Hayes, with Dr. Skalk Yenes, with Marcus, with all of those people. The information, the skills that we have shared with all of us, even today, really, Prof, we really appreciate that. We really remember all of that in our line of work every day when we engage in electrical engineering in various ways, especially in load research. And some of us are trying our best to get the young people, to also be part of load research so that we can be able to hand over the baton also to the new generations also, so that this type of work can be able to be carried forward. So we thank you very much, Prof, for spending the afternoon time with us. It's really appreciated. Karen, would you like, or Wayne, would you like to also say something before we let go of Prof? Any other member, by the way, you're welcome. We can use the 2 minutes before Prof, we let go of Prof.
Thank you. I just also want to say thank you very much, Prof. It was really interesting and inspiring. And as Alison also said, it's inspired her as well to do some deep thinking. And yes, it is good to just to think what we've learned so far. And it also just shows what an interesting field and an interesting career choice we are in, career field. Thank you.
Yeah. Thanks, Prof. Any parting shots, Prof? Thank you, members, all for connecting. Prof, your last word?
Very quickly, I think Karen makes an excellent point. There are young engineers coming up, and we can show them what an interesting field this is to be in. And if you think of battery energy storage systems, we're talking of moving to very large sizes. And there are losses as the energy comes in, and there are losses as the energy goes out. And we really need to optimize that because we're talking about thousands or millions of rands. And this is where people can make a difference. So this is a profession in which people can make a difference. And I've found it exciting in the past, and maybe it's getting even more exciting in the future. I wish you all the best, all of you.
Thank you very much, Prof, for those kind words. Thank you, colleagues. The meeting is adjourned. The time now is 16:08. We really appreciate it. Thank you for connecting, all of you. Take care. Bye-bye.